Everyone, welcome to the course of Electrical Machine 1. This is Abhishek Singh, Assistant Professor at Engineering from Banswara. So, in Electrical Machine 1, we'll start with the DC machine. Later, we'll discuss the transformer part. Okay. So, today we'll start with the DC machine. So, when we talk about DC machine, it's a common term we use both for DC generator and DC motor because the construction is same. The principle of operation is different. So what DC generator is? When we talk about DC generator is nothing but a device which use the principle of electromagnetic induction to convert a mechanical energy into an electrical energy. Device which use electromagnetic induction principle to convert mechanical energy into electrical energy. Okay, so this is basically a DC generator. So in 1831, Faraday's was doing an experiment on electromagnetism, and he proposed two laws: Faraday's first law and second law. And in 1831 only, he developed a DC generator which was around 1.5 kilometer of radius, very big. And in later in 1880, the first power plant established in the Pearl Street of New York. Pearl Street of New York by Thomas Alva Edison. Okay. So what was the two laws of Faraday's? What was the two laws of Faraday? The first law was what? If there is a conductor between flux, or if there is a flux cutting by the conductor, then there will be an induced EMF in the conductor. Okay. So if there is a flux linkage with the conductor, then the EMF will induce in conductor. EMF, motive force, will induced in conductor. Okay, this was the first law of Faraday's electromagnetic induction. Second law was the second law. The induced EMF E is directly proportional to time rate of change of flux or flux linkage. Okay, so the principle of DC generator is based on the Faraday's laws. So let's first discuss how many type of flux linkages are there. Okay, so here we have general three possibility by which a flux link with a conductor. Suppose let's discuss the flux linkages. First possibility is what? If our flux is stationary, okay, flux stationary, and your conductor is rotating, then there will be a flux linkage, and the EMF induced here, we'll call it as dynamically induced EMF. Dynamically induced EMF. Okay, and this happen in your DC generator. Okay. Second type of flux linkage, your flux is rotating. Flux is rotating, and your conductor is stationary. In this case, also there will be a flux linkage, and the induced EMF again will be a dynamically induced EMF, and it happens in your AC machine, AC generator, or the synchronous generator or alternator. Okay. Third, what? Your flux and conductor both are stationary. Flux and conductor both are stationary, but here your flux is time varying. Okay. In these two cases, your flux was constant. It was stationary and revolving physically, but it's not time varying, it's constant. Here in third case, the flux is stationary, conductor is also stationary, but flux is time varying. In this way, there could also be a flux linkage, and the induced EMF here will call it as a statically induced EMF. Okay, this happens in our transformer. Okay, okay. Now let's come to the principle of operation of DC generator. Let's discuss principle of operation. So here, if we have suppose north south pole, can be a permanent magnet or electromagnet, I think. Okay. So here we have a stator part, like north or south. Four poles will be developed in a stator part, and if we have a conductor in between these poles, if there is a pole, there will be a flux like this, north to south. Okay, and if we have a conductor here rotating in this flux, let's say rotating in clockwise direction, means we are applying a mechanical input to this conductor and it's rotating in clockwise direction, then there will be an induced EMF by the Faraday's first law. Okay, and it will be your E is equal to n d phi by dt, when n is the number of conductor, or you can say Z here also, d phi by dt. Okay, or it's a formula here, VL sine theta, which is the flux density, velocity, length of conductor, and theta is the angle between coil and flux axis. So the coil is rotating 360 to time, and when it is a position where this coil axis is parallel to the flux, then your theta angle will be 0 and your induced EMF will be 0. And when it is perpendicular to the your flux, then the theta will be 90 and your induced EMF will be maximum. When it is 0, means this theta is 0, and the coil is parallel to the conductor is parallel to the axis. This position is nothing but your magnetic neutral axis between the poles, and where this theta is 90, this is the polar axis on the poles. So when it is parallel, your induced EMF will be 0, then it will increase gradually, and at is equal to 90. It will maximum, then it will decrease in will maximum in negative direction. This way you'll get an AC voltage here. But we are going to discuss a DC generator. So what next we'll do, we'll collect this AC with the help of a commutator segment. This commutator segment, role of this commutator segment is nothing but to convert this AC into DC. So here with this we'll collect with the help of brushes, we'll collect our DC here. Okay. So these commutator segment are doing what? Converting the DC into AC. So how they are converting it? It's a diagram. This is flux conductor. Suppose the direction of current is like this. Okay, and this is your commutator segment A and B. तो जो भी आपके commutator segments हैं, ये करते क्या है? इस मैकेनिकल अरेंजमेंट है, ये आपके कॉइल के साथ कंडक्टर के साथ रोटेट हो जाते हैं, तो आपका जो है करंट डायरेक्शन है वो ये आउटर सर्किट में यूनिडायरेक्शनल चलता रहता है. सपोज ये डायरेक्शन के हिसाब से करंट आपकी इस तरह से फ्लो होगी. नेक्स्ट साइकिल में जब ये कंडक्टर, लेट्स से दिस इज ए बी, दिस इज सी डी, इंटरचेंज हो जाएंगे लाइक दिस. This is your now CD and this is your AB. Okay. Now your current direction is like this. Okay. अगर आपके यहाँ पे कम्यूटेटर सेगमेंट चेंज नहीं होते, अगर ए बी एज इट इज रहते, तो सी डी तो किससे कनेक्टेड था? बी से. तो सी डी आपका ये बी से कनेक्टेड रहता, तो ये ए से कनेक्टेड होता. ठीक है. और करंट डायरेक्शन आपकी, करंट डायरेक्शन ये ऐसे है, करंट डायरेक्शन आपकी अभी रिवर्स हो गई होती. ठीक है. यहाँ से ये इधर आता, तो यहाँ से जो करंट निकलती वो इस तरह से जाती. ठीक है. यहाँ से ये कनेक्ट होता है इधर ए बी, ए से. लेकिन ये कम्यूटेटर सेगमेंट क्या करता है, ये अपने आप भी पोजीशन चेंज कर ले रहा है. तो इस तरह से जैसे ही आपका डायरेक्शन इसमें ए बी सेगमेंट बदलेंगे, ये खुद भी चेंज हो जाएगा. ये बी इधर, ए इधर, सी एंड. इससे क्या होगा आपको, अगेन यूनिडायरेक्शनल करंट इन दिस डायरेक्शन ओनली आप कलेक्ट कर सकते हैं विद हेल्प ऑफ दिस ब्रशेस. विल डिस्कस लेटर द ब्रशेस. ओके. तो अगर चेंज नहीं होते इस ए बी तो क्रॉस हो जाता और हमारा करंट की डायरेक्शन चेंज हो जाती. बट क्या हो रहा है कि ये ए कॉइल के साथ, कंडक्टर के साथ ये सेगमेंट्स भी अपने इंटरचेंज हो रहे हैं, तो हमारा यूनिडायरेक्शनल करंट हमको मिल रहा है. तो द रोल ऑफ दिस कम्यूटेटर सेगमेंट्स आर नथिंग बट टू कन्वर्ट आवर DC into AC. So these are basically the mechanical rectifier, you can say. Okay. Okay. Now let's discuss that this induced EMF, the direction of the induced EMF will be decided by Fleming right hand rule. So direction of E will be decided by Flaming right hand rule. Okay, so according to Fleming right hand rule, the direction of induced EMF when you are in the influence of south pole will be positive, and it will be negative you are in when the conductor are in uh, north pole region. Okay, so here under the south pole, your induced EMF will be positive, and here the north pole it will be negative. Okay, okay, fine. Then you discuss the construction one by one. Okay, so first let's discuss about the stator. Stator, where we will produce the operating flux. So nothing but it's a yoke. Let's draw the yoke. Okay. Here we have a holes like structure. Holes like that. Like that. So these are the poles shoe. Here your north south alternate north south pole will be developed. This is your nothing but your yoke. Yoke is to support the field winding, support the structure, and to provide a path to the operating flux. Means here your flux will provide a complete path to the flux. Okay, like this. So here will provide a DC supply in this pole, and according to the direction of current, the north-south pole will be developed. Okay, so this yoke material for the small machine, we use cast iron. For large one, we generally use the steel structure. Okay, and we use laminated one only to reduce the eddy current losses. Okay, so if we draw this pole separately, it will be like this. So this portion where the your field winding is connected will apply a DC here. Here, this is called the pole core, and this portion down here is called pole shoe. Okay, and this is your pole arc. Call it a pole arc. Okay, uh, now let's discuss the armature core. So armature core and armature winding. Talk about armature, nothing but a cylindrical structure, drum type structure with open slots in them. There are some open slots. They're open here. It looks like a closed slots. You will draw an open slots like this. Okay. So in these slots we have armature winding. In these open slots we'll have an conductors here. Okay, and this core, you see this core portion is made up of silicon steel, and it is also obviously a laminated one. we use the laminated one to reduce the eddy current losses, and it is of silicon steel. Okay, silicon is used to reduce the conductivity because steel has a high conductivity. Reduce the conductivity, but it does not affect the magnetic property. But we are restricted to use only 4% of silicon, because if we use more silicon, then your mechanical stability will be disturbed. Okay, 4% silicon. Okay, then we uh, want a armature winding here in this slots. Okay, okay, so now let's discuss the armature winding. Okay. Armature winding, we have two type of basically armature winding. It's a we use the generally distributed and full pitch winding. The armature windings what we use in DC is full pitch and distributed on periphery. Full pitch means there is a term called pole pitch and there is a term called coil span. Pole pitch is nothing but pole pitch is nothing but the distance between pole or number of conductor between pole we can say, and coil span is nothing but the distance between two coil sides. Okay? This is clear. Coil span nothing but distance between two coil sides. Suppose we have a coil here, two conductor, one coil side is this, one is this, so this distance is your coil span. Now what is pole pitch? The distance between two poles, two adjacent poles, not south pole, the pole pitch. Okay, distance between poles. So if your coil span is equal to your pole pitch, then your winding is a full pitch winding. So if your coil span is equal to pole pitch, then we call it as full pitch winding. And this type of winding we use in DC. DC. Okay. When this coil span is sorted, coil is sorted by some slot angles. Your coil, when your coil span is less than your pole pitch, then we call it as a short pitch. And this type of one winding we use in alternator, DC generator, synchronous generator. Okay. Okay. So we generally use two type of winding. We'll discuss. So the first is lap winding, and second is your wave winding. Two type of winding we use in DC circuit. Okay. So lap winding, if we draw roughly, will be like goes here segments. So it will be like two. 3, like overlapping like this. Drawing it roughly, it will be like this. Okay, so we generally call it a parallel winding. Okay, and this wave winding is this type of sense of one pole. Second. So this winding is like this. So we generally call it as a series winding. Okay. So number of, if we talk about the number of parallel path, the number of parallel path A here is equal to number of pole, and here number of parallel path A is equal to 2. Okay. So actually our winding is connected in the terms of a formation of the parallel path. Like if we have let's say 24 conductor with the 4 pole, and if we are using the lap winding, the windings are in parallel path. So if we have 4 pole, then we'll have 4 parallel paths here like this. So if you have suppose 16 conductor per parallel path, so in each parallel path you will have a 4 conductor. Okay, 16 conductor, total 16 conductor suppose you have, and for per parallel path you will have a 4 conductor at least. Okay, because here in lap winding your parallel path is equal to number of pole. Okay, suppose you have 60 conductor and 4 pole machine, so it will be like this. Then EMF induced per conductor, suppose 1 volt, 1 volt. Okay, so what we'll get here, the voltage here 4 volt. There are 4 conductor in one path, they are connected in parallel, so the number of so voltage here will be 4 volt. Okay, so now if 1 ampere current produced in one parallel path, then there are 4 paths. The current I will be 1 plus 1 plus 1, 4 ampere. Okay, 4 ampere. Now what will happen in this wave winding? Here number of parallel path is 2 only. Okay, now you have 16 conductor and you have only 2 parallel path, so you will have an 8 conductor per parallel path. Okay, if one conductor have 1 volt, then you will get an 8 volt voltage here, and in one parallel path if 1 ampere current is flowing, then you will get here the 2 ampere. So what you can see in parallel in lap winding, the parallel path is equal to number of pole. Okay, so here the current will be more and your voltage will be less, and here your voltage will be more, your current will be less. So here the lap winding call it so low voltage high current. Low voltage high current winding, or this is high current high voltage and low current. Okay, so if we have a wave winding, then the rating will be high voltage and low current. We have lap winding. So from here you can conclude that your current is proportional to your parallel path and your voltage is inversely proportional to parallel path, because here parallel path is more, voltage less. The parallel path is less, voltage is more. ओके, तो इस पे हमारे न्यूमेरिकल कई बार कंपटीशन में बहुत ज़्यादा आते हैं, ठीक है, कि आपके लैप वाइंडिंग थी, इसको वेव वाइंडिंग कर दिया, तो पहले वोल्टेज इतना था, अभी कितना हो जाएगा। रेजिस्टेंस से क्या होता है, लॉसेस अगर सेम रहेंगे तो आई स्क्वायर आर इज इक्वल टू, लेट्स से आई स्क्वायर आर हम लिखें, तो ये लैप वाइंडिंग है और वेव वाइंडिंग है, ओके, तो क्या होगा, आर एल बाई आर वेव इज इक्वल टू आई वेव बाई आई एल का स्क्वायर, एंड आई वेव बाई आई एल, करंट जो है वो डायरेक्टली प्रोपोर्शनल है, तो इसका मतलब आर एल बाई आर डब्ल्यू मीन्स लैप वाइंडिंग में रेजिस्टेंस डिवाइड बाई वेव वाइंडिंग का रेजिस्टेंस इक्वल टू पैरेलल पाथ इन लैप वाइंडिंग डिवाइड बाई पैरेलल पाथ इन वेव वाइंडिंग का स्क्वायर। कुछ रिलेशंस भी हम याद रखेंगे। वोल्टेज की बात करेंगे तो वोल्टेज इन पैरेलल पाथ मतलब वेव वाइंडिंग लैप वाइंडिंग रिलेशन जिसका इन्वर्सली प्रोपोर्शनल है पैरेलल पाथ से। वोल्टेज के टर्म में अगर हम इसको लिखना चाहें तो क्या लिखेंगे, वोल्टेज के टर्म में अगर आप इसको लिखेंगे फॉर्मूले को, तो आप लिखेंगे वोल्टेज इन लैप वाइंडिंग डिवाइड बाई वोल्टेज इन वेव वाइंडिंग इक्वल टू पैरेलल पाथ इन वेव वाइंडिंग डिवाइड बाई पैरेलल पाथ इन लैप वाइंडिंग। You know the parallel path in wave winding is 2 and the parallel path in lap winding is equal to number of pole. Okay, so this relation helps a lot solve numerical. तो कंपटीशन में भी ऐसे बहुत सारे न्यूमेरिकल आपके सीधे रिलेशंस पे आते हैं। okay? तो ये हुए वाइंडिंग्स की बात। अब कम्यूटेटर सेगमेंट की बात कर रहे थे हम। वाइंडिंग्स के बाद वाइंडिंग हमारी जो है वो किससे कनेक्ट होती हैं, कॉइल्स कम्यूटेटर सेगमेंट से। कम्यूटेटर सेगमेंट हमको पता है कि टीसी हमारे एसी को टीसी में चेंज करेंगे। these are like this, these are basically the reflection of our coil. Okay, we have kind of segments, and your coil sides are shouldered in this segments like this. So the number of coils are equal to number of commutator segment. Commutator segments. Okay, and here we have brushes which collect the currents. Okay, so when we talk about the brushes are nothing but to collect the currents. So brushes are generally made up of carbon, copper or graphite. And these brushes are generally held in a brush holder and they spring their spring brush holder. We call it as a pigtail. The structure is like that. So the role of brush is collect the current from the armature or from the commutator segment sparklessly, safely collect the current. Okay. So role of brushes to safely collect the currents. तो स्पार्किंग नहीं चाहिए तो ब्रशेस हम यूज करते हैं। तो हम जनरली जिसकी रेजिस्टिविटी रेजिस्टेंस हाई होगा वो उसको यूज करेंगे ताकि कम्यूटेशन हमारा आगे बहुत प्रोसेस है आर्मेचर रिएक्शन में कम्यूटेशन हम पढ़ेंगे थोड़ा डिटेल में ब्रशेस और कम्यूटेटर सेगमेंट्स। तो ये आपका ओवरऑल एक कंस्ट्रक्शन पार्ट हुआ प्रिंसिपल का, फिर के कौन कौन से कंपोनेंट हैं और वाइंडिंग के क्या क्या है, तो लैप वाइंडिंग वेव वाइंडिंग में। नेक्स्ट वी विल डिस्कस द ईएमएफ इक्वेशन, फिर उसके बाद कितने टाइप ऑफ डीसी जनरेटर्स हैं और कैसे कैसे उनका कंस्ट्रक्शन है।